Welcome to The Explainer. Today, I'm going to be stepping into the role of your professor to explore an absolutely fascinating feat of modern engineering. We're going to dive into the critical mechanical and chemical processes designed to clean industrial exhaust and protect the air we all breathe. We'll be looking closely at the exact science, the physics, and the chemistry that make our modern industrial world possible without completely choking our skies.
Okay, let's look at our syllabus for today. We've got 5 key topics. Number 1, the pollution problem. Number 2, gravitational and inertial separation. Number 3, physical filtration systems. Number 4, electrostatic precipitation. And number 5, wet and dry scrubbing.
Section 1. The pollution problem.
So, to understand how we clean industrial exhaust, you first have to recognize that contaminants aren't just uniform. They come in wildly different states and sizes, meaning no single physical force can capture them all. We have to engineer a sequence. You might be wondering, how do we actually capture massive, heavy dust particles efficiently? Well, for the heavy, visible soot and dust, we turn to the most universally understood physical force at our disposal: gravity.
Which brings us to Section 2, gravity and inertial separation.
For this macro-scale dust, we manipulate the actual environment the dirty air travels through. Take a look at how a gravity settling chamber uses basic physics to its absolute advantage. Inside the chamber, the dirty gas encounters a series of baffles and trays. These physical barriers intentionally disrupt the airflow, slowing the dirty gas way down. And by dropping that velocity, we literally just let gravity do the heavy lifting, pulling those large particles downward out of the airstream.
The mechanics here are beautifully simple and incredibly effective as a first line of defense. Step 1, you introduce the high-speed dirty gas. Step 2, you intentionally drop the velocity using those baffles. Step 3, you let the heavy particles fall directly onto the trays and into the hoppers below. And Step 4, the partially clean gas exhausts out the other side, ready for the next stage. But that brings us to our next engineering hurdle. Gravity works wonders for heavy particles for sure, but what about the fine particles? The ones that are just way too light to fall before they exit the chamber? When gravity isn't enough, we actually have to artificially amplify the forces applied to the particles. And that is brilliantly solved by the cyclone separator. This thing operates basically like a giant spinning carnival ride. It introduces the dirty gas at an angle, forcing it into a tight vortex. This swirling gas generates a massive centrifugal force that literally throws the particulate matter to the outer walls, completely bypassing the limitations of simple gravity. Let's break down exactly what's happening here. First, the dirty exhaust gas enters tangentially, which forces it to spin. Second, that swirling gas stream generates our centrifugal force. Third, because the particles have more mass than the air, they are forced to the outside walls. Fourth, they lose momentum and drop straight down to the collection base. And finally, the resulting cleaner exhaust gas spirals upward and right out the top. Okay, but how do we capture particles that are literally too small for a cyclone to push outwards? Down at a fraction of a micron, even that amplified momentum isn't enough. The particles just flow right out with the air. At this stage, we have to ditch motion and gravity entirely and transition to using physical barriers.
Section 3, physical filtration systems. Consider the fundamental principle of the fabric filter baghouse. Even though this operates on a massive industrial scale, the core concept is actually exactly like a giant vacuum cleaner bag. Inside the enclosure, there are rows and rows of cylindrical fabric filter bags. The system forces the air through the incredibly tight weave of that fabric, physically blocking the microscopic dust.
Here's the highly systematic operational sequence. 1. Dusty air enters the lower inlet. 2. The air is forced right through the filter bags. 3. Naturally, the dust becomes trapped, forming a layer on the inner surface. Now 4 is crucial. A mechanical shaker mechanism periodically agitates the bags to dislodge that dust buildup, dropping it into a hopper. And 5. The clean air is expelled continuously without the system getting clogged.
But what about clean rooms, hospitals, or nuclear applications? For the absolute finest particulate matter, we turn to high-efficiency particulate air, or HEPA filters. Now, at the microscopic scale, these filters rely on some incredibly complex physics to capture particles that are actually much smaller than the gaps between the fibers themselves.
The key takeaway here is that a HEPA filter is not just a simple net. It actively uses 3 distinct mechanical principles. First, interception. Particles simply follow the airflow, graze the fiber, and adhere to it. Second, impaction. Slightly heavier particles have too much momentum to bend with the air, so they crash directly into the fibers. And lastly, diffusion. The absolute tiniest particles bounce around randomly. That's Brownian motion, until they inevitably collide with the fiber and get trapped.
So we've trapped the microscopic solids, but what if the polluted gas stream is just way too hot or filled with corrosive elements, like you'd find in metallurgy or power generation? Physical fabrics would literally just melt or corrode away. We need to deploy a totally different physical property.
Section 4. Electrostatic precipitation.
This phenomenal technology removes the need for physical barriers entirely. Instead, it uses high voltage to attract dust, operating exactly like rubbing a balloon on your hair to create static electricity, just scaled up to industrial proportions. The polluted air flows through an array of high-voltage discharge electrodes and grounded metal collection plates. Because there's no physical filter media, it can handle immense volumes of extremely hot gas with minimal resistance.
Here's the physics in action. Step 1. The polluted air passes the high-voltage discharge electrode. Step 2. The intense electrical field actually strips electrons, electrically charging the passing particles. Step 3. Those charged particles are magnetically attracted to the grounded collection electrode, sticking fast to them. And Step 4. A mechanical wrapper strikes the plates, causing the accumulated dust to shear off and fall into the hopper.
At this stage, we've mechanically filtered out all the solid matter. But we're still left with dangerous gaseous pollutants, things like sulfur dioxide. Since they aren't solids, no physical filter or static magnet is going to catch them. This requires us to completely shift our focus from physics straight over to chemistry.
Section 5. Wet and dry scrubbing. Scrubbers are sophisticated chemical systems engineered to neutralize invisible, toxic, gaseous pollutants before they can reach the atmosphere and cause things like acid rain. They generally fall into two classifications: dry scrubbers, which use dry injection, evaporative coolers, and a downstream baghouse, and wet scrubbers, which utilize packed beds, recirculation pumps, and scrubbing liquid spray nozzles to literally wash the contaminants out.
Comparing the two setups directly, you can really see the profound engineering differences. A dry scrubber system uses a dry injection line to mix a reactive, neutralizing power right into the gas stream, which is then safely captured by a downstream module baghouse. A wet scrubber system, however, forces the gas upward through a packed bed, which maximizes the surface area, against a heavy downpour of neutralizing liquid from spray nozzles.
We've journeyed through an incredible gauntlet of applied science today. From harnessing simple gravity in settling chambers to using inertia in cyclones, exploiting microscopic diffusion in HEPA filters, manipulating static electricity, all the way to complex chemical scrubbing. These engineering marvels act as our invisible shield, operating relentlessly to protect the air we breathe. Understanding this level of mastery over physics and chemistry really leaves us to wonder, what other massive environmental threats can brilliant engineering solve next? Thank you so much for joining me for this explainer, and I'll catch you next time.